Let's examine how the different interframe spacings are applied in CSMA-CA, as well as how RTS and CTS manage and coordinate to prevent other terminals from communicating. The 802.11 standard specifies that the physical layer's air interface must listen for carrier signals. When a STA sends its first MAC frame, if the channel is detected as free, it waits for a DIFS period before beginning to transmit the first frame, initiating the request. After sending RTS to the AP, having received RTS, cannot respond immediately and must wait for a CIFS, as all frames in a wireless network must wait for an interval before sending an acknowledgement. After the CIFS, the AP responds with a CTS, and then waits for another CIFS. However, note the presence of other STAs. What are they doing? When the first terminal sends an RTS, nearby STAS also receive this RTS and begin to back off, entering a sleep mode. When a STA detects the duration field in the header of a MAC frame being transmitted on the channel, it adjusts its network allocation vector, NAV, which indicates how much time must pass to complete the transmission of the data frame and return the channel to a free state. Secondly, when the AP receives an RTS, it sends a CTS. After the CTS is sent, if other STAs, like STA2, are far from STA1 and can't receive STA1's RTS, they might still transmit wireless data. But it's okay because the AP sends a CTS, indicating to all terminals within its range to back off, thus generating a second NAV, preventing further data transmissions by other terminals. Looking at the first STA, after receiving the CTS from the AP, it waits for a CIFS before transmitting data. After completing the data transmission, it waits for another SIFS, signaling the completion. Then the AP sends an ACK acknowledgement, and at this point, the channel is freed up for a new cycle of message transmission. Why is my STA the one sending the RTS? There is a contention mechanism, with many terminals needing to compete. Who sends the RTS first? Let's see. After diffs, there's a random back-off mechanism to decide who sends the RTS. Take a look. We have a formula to calculate the slot time for back-off periods, which are multiples of slots, where the sequence of back-off is chosen from 2 raised to the power of 2 plus I, where I is the number of back-offs. The first time is 2 raised to the third power, which is 8 slots. Each terminal randomly selects from the 8 slots, e.g., the first terminal picks 8 slots, the second picks 7, the third picks 2, and the fourth picks 3. Whichever terminal finishes its countdown first starts transmitting data. Here, STA3 completes its countdown first and begins transmission, while other terminals' slots are frozen and do not count down. After STA3 finishes transmitting, since everyone has waited 2 slots, STA1 has 6 slots left, STA2 has 5, and STA4 has only 1 left. Then, as STA3 just finished and is in its second back-off, it selects from 16 slots. Suppose it starts from 9 slots. Now STA4 has only 1 slot left and begins transmitting data, while other STAs freeze again. This is the random back-off mechanism in action. This section, combined with previous discussions on RTS and others, forms a comprehensive communication process in a wireless network. This module is intricate, so pay close attention. Now let's revisit the hidden node issue with RTS and CTS. As mentioned before, for example, when Terminal 1 starts sending RTS and the AP receives it, because STA2 is too far, it doesn't know that STA1 has already sent an RTS and continues to transmit data. But then the AP sends a CTS to STA2, which then realizes that another STA is sending RTS and begins to wait quietly. Next, consider the exposed node scenario, which is unique. Here, AP1 communicates with STA1 and AP2 with STA2, which means they actually do not affect each other. However, because they are too close, when STA1 sends RTS, STA2 receives it, and vice versa, significantly impacting each other. because STA2 can receive the RTS from STA1 but not the CTS sent by AP1. This is what we call an exposed node. In this scenario, the AP or terminal responds only to received CTS, ignoring the prior RTS. Therefore, STA2 will broadcast an RTS to reserve channel access, illustrating the exposed node scenario. Next, we look at channel bonding, which binds two adjacent, non-overlapping 20 MHz channels into a 40 MHz channel. Although two channels are bonded, one acts as the primary bandwidth, and the other as secondary. In representation, if channel 1 is selected as the primary, it is denoted as plus mode, and the bonded channel is referred to as 1+, indicating that channel 1 is the primary, and channel 5 the secondary, with a combined bandwidth of 40 MHz. If channel 5 is chosen, it is called the minus mode, where 5- denotes channel 5 as the primary and channel 1 as the secondary for a 40 MHz bonded channel. For 5 GHz channel bonding, 40 MHz is achieved by bonding two adjacent 20 MHz channels, one being primary and the other secondary. For example, if the current channel is 149, to achieve a 40 MHz bandwidth, another channel needs to be added. That is, combining channels 149 and 153 into a 40 MHz bandwidth. 149 plus indicates a 40 MHz channel formed by the 20 MHz channel at center frequency 149 and the 20 MHz channel at center frequency 153. 80 MHz bonding uses center bandwidth to represent. It is specifically reflected, for instance, if channel 149 is standalone, then it's 40 MHz. If it's an 80 MHz bandwidth, additional bandwidth must be supplemented. So, in 5G channel bandwidths, the specific bandwidth must be reflected, including the channel bonding for 2.4G and 5G. Next, we discuss MIMO technology. Here are a few concepts. SISO, single input, single output. Since there is only one path between the transmitting and receiving antennas in SISO, this transmission system is unreliable, and the transmission rate is limited. To change this situation, we tried modifying the terminal by adding an antenna, enabling the receiver to receive signals from two paths, known as single transmit, multiple receive. The second concept is SIMO, single input, multiple output, where there are two paths between the transmitting and receiving antennas, but the data is still transmitted from one antenna, transmitting a single signal. This doubles the reliability, a method known as receive diversity. The third concept is MISO, multiple input, single output, with two paths between the transmitting and receiving antennas, but only one receiving antenna, which means the transmitting antennas can only send the same data, transmitting only one signal, similar to SIMO effects. This transmission system is called multiple input single output, also known as transmit diversity. MIMO technology allows multiple antennas to simultaneously send and receive multiple spatial streams, i.e., multiple signals, and distinguish signals heading to and coming from different spatial directions. By using spatial multiplexing and diversity techniques, it increases system capacity, coverage, and signal-to-noise ratio without increasing bandwidth. When transmitting data, it depends on the endpoint with the fewest spatial streams, which is why it's often said that when purchasing terminal devices, the more antennas, the better, as they support more spatial streams, enhancing your signal transmission capabilities. What then is MU-MIMO? On the left is a non-MU-MIMO scenario, for example, with a bandwidth of 20 megabits per second, where these three terminals each have 20 megabits per second bandwidth and can only send data to one user at a time. On the right, with MU, the AP has 300 M, and the three terminals share the AP's bandwidth, but it can send data to multiple users simultaneously. This is multi-user multiple input, multiple output, MU-MIMO. How is this achieved? Although these are different users, I can treat them as one device with 3 antennas, allowing the AP to communicate simultaneously with one user as if only 3 antennas are operating. In 802.11 AC, there is downlink MU-MIMO, which is multi-user parallel downlink. The AP differentiates the data for specific hardware facilities when sending data to terminals, similar to parallel grouping. This is a specific implementation of MU, treating multiple devices as one for operation purposes. In 802.11ac, it was only possible to implement downlink. In 802.11x or WiFi 6, both uplink and downlink MIMO have been realized, greatly enhancing the efficiency of multi-user concurrent transmission, which is a core concept of Wi-Fi 6. Next, let's look at beamforming, which is related to phase enhancement and attenuation mentioned earlier. Because the transmitter has multiple paths, if signals of different phases are transmitted together, phase attenuation occurs. Beamforming automatically adjusts the phases to ensure signal enhancement without signal reduction, increasing the signal-to-noise ratio. This is the concept of MIMO beamforming. Next is the BSS coloring mechanism in Wi-Fi 6. BSS, Basic Service Set, is the basic unit of WLAN, consisting of a fixed AP and multiple terminals. When AP1 and STA1 are communicating within a service set, and there's another nearby BSS with AP2, this is called Overlapping Basic Service Set, OBSS. OBSS can cause STA1 to back off, hence the introduction of a BSS coloring mechanism, which adds a BSS color field in the PHY frame header to differentiate data from different BSS, assigning a color to each channel that signifies a group of basic service sets that should not interfere with each other. The receiver can then early identify co-channel interference signals and stop reception to avoid wasting transceiver mechanisms. If the colors are the same, it's considered as interference within the same BSS, and transmission will be deferred. If the colors differ, they are considered interference-free, and 2 Wi-Fi devices can transmit in parallel on the same channel and frequency. The last one is TWT, target wake time, the previously mentioned power-saving mechanism. Without TWT, everyone is awake. With TWT, the AP will tell the terminal when it can sleep, and then provide a wake-up schedule. Sleep times are very short, just a few microseconds each. Although each sleep period is short, repeated sleeping significantly extends the device's battery life, as Wi-Fi functions consume about 30% of battery power. TWT was first introduced in the 802.11n standard, originally designed as an energy-saving mechanism for IoT devices, especially those with low activity levels, such as smart meters, allowing IoT devices to remain asleep for as long as possible to achieve extremely low power consumption. After establishing the TWT protocol, stations no longer need to receive beacon frames, but operate on a much longer cycle instead. The 802.11 AC standard improved this by introducing rules for station behavior, achieving channel access control under the premise of energy conservation, which is what the TWT technology is about. We have primarily introduced the basic concepts of wireless communication, the 802.11 standards, and key WLAN technologies. In the next lesson, I will explain the WLAN networking model. Thank you, and see you in the next class.